Special relativity. Now, again, I'm going to make this simple for the lay audience. I'm not going to discuss all this, but I'm going to discuss one or two really interesting features of it. It is what's called time dilation and length contraction. And it's the idea that objects that are moving away from you at a certain speed actually measure time and distance in ways different we would measure them, which is very, very strange, but it's true. I want to show you how these result from a simple logical argument. I will have a little math, but you can just skip over that part because I want to highlight the logical significance of this. In the late 1880s, we didn't know whether the speed of light was a constant. Maxwell's equations sort of suggested it, but we didn't know. So there was a very famous experiment in 1887 by scientists Michelson and Morley that showed, more or less, that the speed of light is a constant. So the speed of light, we'll call it c, is about 300 million meters per second. It's very fast, but it's a constant. And what I mean by constant is that I would measure the speed of light at this speed, but if you were moving away from me very, very fast, you would also measure the speed of light at this exact same speed. And the reason that seems weird, or it should seem weird anyway, is that if I throw a ball at a speed of, I don't know, 10 units, 10 meters per second, 10 miles per hour, whatever you want, at a rate of some speed of 10, and you're moving away from me at a speed of 5, whatever that is, 5 meters per second, and you also throw a ball relative to you at 10 meters per second, well, how fast would I measure it? I would just add those together, 5 plus 10, because you're moving this way and throwing the ball, so the ball would seem even faster to me, right? It would seem like, from my perspective, you've thrown the ball at 5 plus 10, 15 meters per second. So ordinarily, these sorts of things would add or subtract. They wouldn't be the same. So what's weird, though, is that if instead of throwing a ball, I shoot a ray of light that goes at the speed of c, and you're moving away from me at some speed, 5 something meters per second, and then you shoot light away from you that you measure as a speed of c, then you would imagine that I would measure it as 5 plus c, right? It would seem like the light is moving even faster relative to me because you're moving away and shooting the light, so it should give the light a boost to go even faster, right? But that was the whole point, is that was what was discovered in 1887, more or less, was that that's not true. Was that even though I measure the speed of light at c, as c, and you, who are moving away from me at some speed, also measure light at the speed of c, that I would measure your light beam as going not 5 plus c, but just c. So the speed of light is a constant in every inertial frame. Inertial frame means there's no acceleration. So that was a really strange thing to discover in the late 1800s. So let's say that you start with the knowledge of, number one, the speed of light, we'll just call it c, is constant in any frame, any reference frame, any inertial frame. What I mean by that is that there's no acceleration. So this already was a strange idea. 2, the laws of physics shouldn't care about whether I'm moving or not, or at least moving at a constant speed. So the laws of physics should be the same in any frame. This statement is called classical relativity or Newtonian relativity. It simply means that if I'm going to do some experiment here, or if at the last minute I realize, oh, I'm late for an appointment in another city and I'm going to take the train, I'll just do the experiment on the train, right? That should be fine. It shouldn't be a problem. So I'm just going to take the experimental package onto the train with me, which is moving, but I should still be able to do the same experiment and get the same result. This was the thing that was really strange, was that the speed of light is the same in any speed frame or inertial frame of reference. So that is the strange part. Now, let's say this is all you have, this and this. Can you figure out special relativity from those? Well, for the most part, you can, and you certainly can figure out these two. It's really amazing. I'm going to show you how it's done. Now, I want to point out that what I'm about to do, this was known more or less in the late 1800s, even 1887. And yet it took until 1905 for Einstein to publish a famous paper on special relativity. I think it's on the electrodynamics of a moving body, something like that. So why did it take 18 years for somebody to take these two things which were already known and produce special relativity? Well, the answer is Einstein gets too much credit for that particular piece of the puzzle. Now, Einstein gets full credit for general relativity, but in terms of special relativity, Einstein was standing on the shoulders of giants. So, for example, George Fitzgerald proposed length contraction already in 1889. Hendrik Lorentz proposed in 1892. The things I'm about to show you were more or less known, or at least there was a hunch about them, very soon after this was realized. But I suppose it wasn't really formalized or really understood at a fundamental level until a couple decades later. Okay, we're just going to start with these two facts. A constant speed of light in any inertial frame, and Newtonian relativity, that the laws of physics should be the same in any inertial frame. And we'll just do a simple thought experiment. And it's this. Let's say that I am going to take a light beam right here, and I'm going to shine it in this direction. I'm going to bounce it off of a mirror so that it bounces back this way, and then I'm going to measure it. I'm going to detect it at this point and see how long that took. Also, I'm going to do the same thing. We can call this the x direction and the y direction. I'm going to do the same thing here. I'm going to shine light this way, reflect it off of a mirror, and then measure it back here. I'm going to call this length right here, we're going to call this length L. I don't know what this length is yet. No, that's not true. Here's also what I'm going to do. I'm going to call, in the laboratory, I'm going to call this length, we'll just call it maybe L star. And what I want to do is I'm going to shoot both of these rays of light. I'm going to start them at the exact same time, and then I'm going to measure when they arrive and see whether they arrive at the same time. Now, if these two lengths are the same, then they should arrive at exactly the same time, right? So if L equals L star, then the total trip time should be exactly the same. That's not complicated. But now here's what I'm going to do. Imagine if this entire laboratory is moving in this direction, a velocity of v. And I'm standing here. My lab assistant is in this laboratory that's moving at speed v, but I'm standing here. I want to ask a question. I want to ask, how long does it take for the beam to make the round trip? Well, my lab assistant in here, to find the total time, so the length is just going to be equal to the speed of light times the time in the x direction. So the total time in the x direction, we'll call it tx. The length is equal to c times, but if I'm going to call it the total distance, that's the total time it takes to go that distance, it's really 2L. So I'm going to divide, I'm going to cross multiply here. So the total time for the light to travel from here to here is just going to be equal to c over 2L. That's what my lab assistant says is the time it takes for the light to go from there to there. I'm standing out here. Do I measure Tx as the same value? Well, classically, we'd say, of course we'd say it's the same. But because the speed of light is constant in all inertial frames, it's going to be different. It's very easy to show this. And here's how I show this. So this entire laboratory is moving in this direction at a velocity v. I'm standing here. So when I watch, or according to my perspective, the light ray is not actually going like this, because the whole thing is moving upward or forward in this direction. So I actually see the light ray do this. So I actually see the light ray do that. I mean, that's it. I hope the light bulb is going off already. The whole system, the lab and my lab assistant, is moving in this direction at v. So according to me, according to my perspective, the light ray doesn't do this. It doesn't take that path. It takes this path. Well, how long is this path? Good old Pythagoras. That's right. So to do that, how far does the light ray travel right here? Well, what we're going to do is look at that as a right triangle where the base is L. The distance that it goes in the y direction is going to be the speed v, or the velocity v, times the time it took to go from here to here. Well, what's that time? It's half of the total time period here. So half of the total time. But here's the problem. It may or may not be the same time. So what I'm going to do is put a little prime there. So the total distance the light ray goes from here to here is then going to be, Pythagoras is going to be the square root of L squared plus 1/2 of this right here. This is the total distance that it goes from here to here. So the total distance is just double that. So this is the total distance that I perceive the light ray went. So the total distance then is going to be equal to the speed of light times that total time that it went. But see, there's the problem, is because the speed of light is constant, you can see that it's going to take longer for it to go this distance. So I didn't need any of these equations really, just to point out that because I see the light ray not go this way like my lab assistant does, but I see the light ray goes this way, which is longer than this, the speed of light doesn't change. Light doesn't speed up to make that path because it has to go further. It's going the same speed. It has to take longer. So already we know that this time that I measure is going to have to be greater than the time that you measure. I mean, already that's a pretty amazing realization. This is time dilation by itself. I mean, yeah, we can work this out, and I will. But what this tells us, the fact that the time that I measure the light to go in that experiment is longer than the time that you measure light to make that round trip path, is called time dilation. It means that, maybe you measure it to be 3 seconds or 3 nanoseconds or whatever it happens to be, whereas I would see that it takes 5 seconds or nanoseconds or whatever. The point is, I observe that that round trip of light takes longer because it's a longer path, and c is constant. So that's time dilation right there. Now let's just work this out really quickly. I'm going to square both sides so I get, multiply by 2, subtract, so we end up getting and then now we take the square root of both sides, and what this tells us is that, so this piece over here has a name, and it's gamma. I think actually Einstein called it beta in his paper, but this is gamma. So the time it takes, as I measure it, is 2L over C times this gamma factor. So you'll notice that these two expressions are actually very similar to each other. So what we have is, what you measure as the total round trip time is 2L over C, whereas what I measure is 2L over C times a gamma factor, and gamma is always going to be greater than 1 because you have something less than 1 in the denominator. So the time that I measure this experiment happening is longer than the time that my lab assistant measures it happening. That's a pretty amazing result. That is time dilation. Now, one thing I want to point out is that time dilation is a very real thing. It's not just appearances. It's very easy to look at this and say, well, it just sort of looks like it takes longer for me, or from my perspective, than for my lab assistant. It's just an illusion. In reality, they're the same time. No, that's not true. Time dilation is a real thing, and I'll give you an example. Cosmic rays are various particles that come from deep space. Sometimes they're pions, and those pions interact in the atmosphere to create muons. Now, muons are particles that are very unstable. They decay very, very quickly, and I think the half-life of a muon is about 2 microseconds. So it decays really, really quickly. By the time a muon coming from the top of the atmosphere and goes through the atmosphere, by the time it would take to get to sea level, muon shouldn't exist anymore. It's something like 50 half-lives in that period. So muons shouldn't exist at all because they decay so quickly. Right when they're made, they almost instantly decay into something else. So we would almost never expect to see a muon at sea level from cosmic rays. Well, it turns out we see lots of them at a far higher rate than we would expect classically. And why is that? It's because the clock of the muon is slowed down by time dilation. Because they're moving so fast, they're usually moving at close to the speed of light relative to us, that there are relativistic effects that we have to include. And when you include time dilation, the fact that the muon measures time more slowly than we measure it, then it lasts longer. So this is just one of 1,000 examples of how time dilation is not just an appearance. It's a real measurable feature of the universe. We derive this purely from logic. The fact that it takes longer, that the time that I measure is longer than the time that my lab assistant measures, was a purely logical argument based only on these two facts. Isn't that amazing? Now, the last thing I want to show you is length contraction. Okay, so length contraction is this. My assistant measures both of these lengths to be exactly the same. So this is what my assistant measures. And my assistant measures that both of these light rays are emitted and reflected back and received at the exact same time. And so my assistant does the experiment. And actually, as soon as it happens, wants to make sure that everything is done right. So if the light rays come back and meet at the same time, then my assistant says, gives me a thumbs up. Is very happy. Gives me some sign that the experiment went well. But keep in mind, I'm going to put a little star here again because we don't know whether or not I'm going to measure these two things the same. In fact, maybe instead of a star, I'm just going to put a little prime. So first of all, what is the total time that should be measured here? Again, and I want to know from my perspective. From my assistant's perspective, it's going to be exactly the same, right? The time measured for the round trip in y is going to be exactly the same, 2L over c, because, well, it's L prime, but my assistant measures them as exactly the same. But what do I measure them? So I want to figure out the total time that I would measure this round trip. I'm going to do it in two parts. The first one I'm going to do is the time, say, that I measure it going upward. So it's going to be that length L prime, but notice that because this whole thing is shifting upward, that this mirror is receding away from light at a speed of v. Now, the speed of light isn't changing, but rather this mirror is receding away from the emission source at a speed of v. So it's going to take longer for the light to catch up, according to me. Does that make sense? The light is emitted here in this direction. From my perspective, once the light is emitted, this mirror is moving away, so it has to go further. It's going to take longer to get up there. So instead of dividing by c, it's going to be c minus v. It's sort of as if the light has lost speed. It hasn't lost speed, but rather what's happening is the mirror is receding away, so it just takes longer to get to the mirror. And the same with the downward part. But now, because the light ray now is coming down, but the whole system is moving upward, the light ray takes less time to get to here. So it's just going to be additive. It's going to be c plus v. Now, all you do is the total time is just the sum of these two things. So the time that I would measure that round trip is nothing more than, and if you simplify this, and then this piece right here, I'm going to factor out the c squared from here, and what that ends up giving me is, I'll rewrite it over here, is that the total time that I would measure it is just equal to this. But this, if you remember from before, that gamma constant was equal to 1 over the square root of 1 minus v squared over c squared. So notice that this piece right here is just equal to gamma squared. So that means that what I've shown now is that the total round trip time in the y direction, as I would measure it, is this quantity. The total round trip time, as I would measure it in the x direction, is this quantity. But notice a key feature here. My assistant is on board and has set up the experiment so that if these two lengths are the same and you shoot the ray of light at the same time, they meet at the same time, he says, yes, we've got a successful result. It worked. We have the time that I measure at Tx is equal to the time I measure it in Ty. So my assistant already knows, has figured out that these two round trip times are the same. But what does that say then about the round trip times as I would measure them? Are they the same? They have to be. Now, they may be different than what my assistant thinks or measures, but they have to be the same time because he's going to give me a thumbs up. I'm going to see that. We're both going to agree that the experiment worked, that we got the same times between these two. Even if I measure them as different times, they have to be the same from each point of view because of Newtonian relativity. The laws of physics, the experiment should be the same and have the same result if it's moving relative to me as opposed to if I'm with my lab assistant. So because of Newtonian relativity, these two times better be the same. So if you plug this in, so we have this, so then what we're going to do now is then we're going to set this time as I measure it in the y direction equal to the time as I measure it in the x direction, which is this. Then you'll see that several things cancel. And what's going to happen is let's get the L prime on one side. So one of those gammas is going to cancel. The C's are going to cancel. The 2's are going to cancel. And what you're going to see then is simply that L prime is equal to L over gamma. That's it. Remember, gamma is a number that's greater than 1, and it's based on that relative motion. And this is length contraction. So the length that I measure this on this moving experiment is actually less than the length than my assistant measures it. And that's necessitated because the times that it takes to do the round trip have to be the same because the experiment was successful according to my assistant and so must be successful according to me. It has to be that the round trip time has to be equal whether we're in this frame or this frame. And so what that requires then is that the length that I measure this is actually less than the length that my assistant measures it. So we've got the two equations. So we've got over here, this 2L over C, this was equal to the original time. So this is the time dilation where the time that I measure it is longer than the time that my assistant measures it because it's adjusted by that gamma. And the length is reduced as I measure it according to what my assistant measures it according to that gamma. So that is length contraction and time dilation solved almost entirely by the logical result of these two assumptions.